Okay, hi guys. So in this lecture, we'll be continuing on seeing some more examples on nucleophilic aromatic substitution reaction. Okay, so let's say we have something like this compound, and we have NO2 on these two positions, and then we are passing it in presence of KOH, and second is in presence of second we are passing a complex compound. Okay, so what actually happens when this compound undergoes the reaction? So what are the possible places at which the nucleophile can actually attack? Obviously one is this and another one is this. We can pick either of the two because both are symmetrical. And okay, I hope you get how we can pick any of the two. Suppose I pick this position and I get this. Okay, and suppose I pick this position and I get something like this. Okay, so what will happen? Suppose I shifted this carbon, I rotated this benzene ring in the same plane with 120 degree anti-clockwise. So what will I be getting? Something like this. This NO2 will come at this position, this NO2 will come at this position, and this X will come at this position. Okay, now in this plane you rotate this compound 180 degree. What will happen? You would get the same compound. Okay, so we can, so hence I say that you can pick any of the positions. So what with the product, we get something like this, and half mole of hydrogen gas is released. Now we have mystery over how this happens, and second mystery is why do we need this as the second reagent. So both the mysteries actually have an interconnection between them. What actually happens is when OH minus actually attacks on this carbon atom, H minus would be relieved. Okay, and what actually happens is we have Fe plus 3 in this case. And how does Fe is plus 3 is showing plus 3 valencies? Because three atoms of or 3 K plus are attached to this complex, so it must be having a minus 3 charge. Okay, and this can only happen because we know that Cn has minus 1 charge over itself. So minus 6 x minus 6 is equal to minus 3, x value is plus 3. Okay, hence Fe is present in plus 3 valency state. So Fe in plus 3 valency state, what it does is it actually act as a oxidizing agent for hydrogen. Okay, it act as a oxidizing agent, thereby reducing itself from Fe plus 3 to Fe plus 2 and forming a free radical hydrogen atom. Now such two free radical hydrogen atoms will combine H2, and only one can be said to have half mole of hydrogen gas released. Okay, now in the next example you need to compare the rate of aromatic substitution reaction in the following compounds. So you have something like this, or this, this and this. Okay, so as you can see, so the rate of aromatic substitution reaction would be highest in this case, because we'll be talking about this carbon atom. This carbon atom is having minus M effect from first NO2 group, minus M effect from second NO2 group, and minus I effect from the Br. Okay, if we talk about this carbon atom, we have minus I effect from the attached Br, minus M effect from the second NO2 group, and minus I effect from the first NO2 group. Okay, in this carbon atom we have only one NO2 group, so we have minus M effect from one NO2 group and minus I effect from the Br group. Okay, and on this we have minus I effect from this NO2 group and minus I effect from Br as well. Okay, so the rate would be something like of the decreasing order. Okay, more the minus and minus I effect, more would be the rate of nucleophilic substitution reaction. Okay, now the second example is about conversion. Okay, you have been given a compound and you have been asked to convert that compound into another organic compound using the reactions which we have discussed over the course of this video lecture series and the previous video lecture series. Okay, so we have something like this and you need to convert this compound into this compound. So how would you actually go about it? I can sense that you have a NO2 group and a OH group attached, and we have already studied that we can actually use nucleophilic substitution reaction by having some OH minus here, and slight bit of heating may be required to get this compound. Now the question is, how will you get this compound? For this compound, again you can say, you can say that NO2 group can be attached when we have nitration can happen in the presence of mixed acid, and if I use this compound, then the nitration can happen at the ortho and para position. Howsoever, this ring is deactivated because of the presence of Br on the carbon or on the phenyl ring, but still nitration would happen on the para position, and on the ortho position it won't happen because of stirring hindrance. Now the question is, how will I prepare this compound? For preparation of this compound, I can use Br2 in presence of Fe. Okay, electrophilic substitution reaction can take place. Okay, so I actually created a whole cycle in which these two are the intermediate products, but ultimately we reach the product somehow using the reagents we studied in the previous lectures or from our memory. Okay, so I hope you enjoyed converting that compound. Okay, so next we have a matrix question. We have a left column and we have a right column. Okay, in the left column, let me first write down the keys of the right column. X is nucleophilic substitution reaction. Okay, and it can be any one of the type either SN1, SN2, SNA, which is SN aromatic, and SN addition elimination. Okay, X is elimination reaction. Okay, WXY is nucleophilic addition reaction, and XYZ is none. Okay, so we have our first. So which of the following compounds, the question is which of the following compounds can show the reactions listed on the right column. So we have something like this, I and NO2 attached here. Okay, so it can show nucleophilic substitution reaction because this is highly partially positively charged carbon atom. Can it show elimination reaction? No. Can it show nucleophilic addition reaction? No. Why? Because it's a so in case when we have to show the nucleophilic addition reaction, some double bond has to convert itself to a single bond. Okay, so in this case the aromaticity has to broken down, and which will not be allowed by the phenyl ring in the normal conditions. Okay, so we won't be marking nucleophilic addition here. We have something like this, CH2Cl, and we have this compound. So will it show nucleophilic substitution reaction? Yes, it can show at this carbon atom it can show SN1. Okay. Elimination, no. Nucleophilic addition, yes. At this position we can have a nucleophilic addition reaction, and the example can be Grignard reagent, reaction of this compound with Grignard reagent. Third compound is, what about this one? Obviously this will show nucleophilic addition reaction. Nucleophilic substitution reaction. SN1 can happen because this positively charged carbocation would be highly stabilized by the resonance. Okay, so it can show W. Can it show X? Yes, it can also show X. Okay. Elimination, it can happen here with this hydrogen atom if we heat it enough. Okay, in the presence of you can have a carbocation formed here, so you can have something like a even mechanism. Okay, solulysis can take place. KOH, you can use some ETOH and heat it, so some solvents can be used. Okay, so nucleophilic addition reaction can take place. No, it does not have a double bond which is not present in the phenyl ring. In the previous case we had a double bond between C and O which was not present in the phenyl ring, because if we use the double bonds from the phenyl ring, it is directly proportional to breaking the aromaticity of the ring, hence we want to go into that. Okay, the last question is, what about this compound? It can show nucleophilic substitution reactions, no doubt about it. It can show elimination reaction. W would be there. Can it show elimination reaction? Yes, we can heat it. Dehydration can take place. Okay. Can it show nucleophilic addition reaction? No scope of a double bond is there, which can be broken up to create a single bond or sigma bond between the incoming nucleophile, hence nucleophilic addition reaction would not take place. So with this we come to an end of this lecture, and from the next lecture we will be seeing an interesting mechanism called benzyne mechanism. Okay, till then, good luck and goodbye.